Welcome back, my structural analysis friends. In today's video, we're going to continue our discussion into determination of deflections or displacements of beams using a method known as the moment area method. So without further ado, let's get started. The moment area method is a classical geometric method for finding deflections of structures subjected primarily to bending. And most of the examples we're going to cover in this class, we always consider just the moment as being the primary variable for the amount that a beam will deflect. Okay, we will not consider shear deformations, which are present and add a small percentage, but we're only going to look at cases involving just the moment, where the moment is a large percentage, and by large I mean like 96-97% of the total of the deformation. Okay, so we're going to neglect shear, we're going to neglect axial deformations. All right, things that we know so far just from our brief discussion and what you may have picked up in your mechanics and materials classes are that we know that a deflection delta is a function of a couple of parameters. It's a function of the bending moment m, Young's modulus E, the material that it's made out of, the moment of inertia of the cross section I, okay, as well as the span, the length L. And these will all be factors that help you derive equations for deflection or displacements. So, and everything we do is going to be built off of assumptions in these and using those as particular tools. Now, the moment area method was created by Christian Otto Moore, and he's credited with this in 1868, although there are others that have been given some credit as well, but he's typically considered the father of it. This is the same Moore that did Moore's circle. All right, so that's it's an oldie but a goodie. So we're 150 years out on this at the time of this video, and it's still applicable today. And I like this method because it's pretty easy if you know how to do the constructions. Okay, and so we'll talk a little bit about what his two theorems that make up this method and kind of the basics for what it is that we're going to do. So we're going to start off with a picture, and there's going to be, I'm going to warn you, it's got a whole lot of lines going off on it. So just like we did in the last video, we're going to start off with just a simply supported beam, okay, and such that this kind of center line here is the undeformed position. Okay, and we know that if I put load on this beam, that it's going to deform to some position, which we're going to denote as this dotted line down here, and you can kind of see it coming here. This method revolves entirely around drawing tangent lines. And you've done this before when looking at slopes. Say, I'm going to define 2 points A and B on the beam, and say at point A, we know that its original position was a horizontal line because it was horizontal here. It displaces down an amount delta A. So that's my A, this is my A prime position, and this is B, and that's my B prime position. And again, we're assuming displacements are still very small, so that this is a vertical displacement. It doesn't have any sort of horizontal shift or anything. Everything is pretty much still vertical. Okay, and then if this is my horizontal line, the references his original position at point A, okay, on the elastic curve, we know that the slope is a line that is tangent to that curve. And so this is the tangent line, and I'm kind of laid it in here. And so you can see that it went from this position to this position. So it went clockwise. And in our definition, that's going to be a negative rotation, but that's the slope at A. Okay, the amount of slope that it underwent. And then likewise at B, we started out here, and if I draw the tangent line to the curve, the tangent line is here. So this time it went counterclockwise, and that will be positive by our basic definition. Okay, and so these are all our kind of how we're going to do it. But everything is all about choosing 2 points on the beam, and how you choose them is part of the strategy of the method. Okay, and then looking at drawing these tangent lines to those locations. So for one, here's the tangent line at A. You see him continuing down to here. And so there's my tangent at A, and then this line here coming down this way is my tangent at B, and you see I labeled it here. And so for the sake of this discussion, we can define the behavior between relative to these 2 points as functions of what's going on with their tangent lines. Now, a couple of things to point out. We've defined previously that the displacement from A to A prime, that is delta A, okay, and B to B prime is delta B. Okay, but there's another one that exists. So if I draw a vertical line through here on this, okay, this point and this point represent something that Moore said that you could calculate, okay, and this is known as a tangential deviation, okay, and the labeling is that this is the tangential deviation at point B with respect to the tangent line at A. And so this difference is actually something that he says that we can calculate. And once I have that, now all of a sudden we start looking for triangles, and I can set up geometric relationships that relate, say, the slope at A to this amount over the length, and all sorts of tricks like that. Okay, so that's kind of what we're looking at. Now, the other thing that we have happening in here is not only the tangential deviations that we're going to be worried about, and I'll show you how you calculate those here in a second. We'll give you the formula, but the idea is that the difference on this drawing, if you drew it to scale or even if you just sketched it, that the difference between these two tangent lines is known as the tangential deviation. Okay, before the tangent line at A was horizontal and the tangent line at B was horizontal, and so that amount was, there was no, the tangential deviation in the undeformed position is 0. That there was no difference in the two, but now because of the effect of the load, it has pushed it, and this amount is a function of how much it's been pushed down. The other formula that he says that we can calculate is the change in angle between two tangent lines. Again, if this is some angle theta A and this is some angle theta B, in the original position they're the same value, they're horizontal, so the change in the angle between the two is 0. And now at the end, after it's been pushed down, because this line has come from here down to here, and this one has gone from here to here, that angle between those two tangent lines is something that we're going to call as delta theta AB. Okay, I know it's confusing. The delta means the difference in theta AB, and this is kind of one of the classic ways of writing it. So we're going to be looking for tangential deviations as well as changes in angles. And the thing that's kind of interesting about this guy is that this is simply going to be theta A plus theta B. Okay. For that angle, right? Because if everything's measured horizontal, it's theta B up, and then it's from horizontal down is theta A, so that difference. Now, one word of warning as we look at this, we've got to be kind of careful of the signs of things, okay? And so this is kind of almost like we're looking at magnitudes of these two values, because it is possible that if I choose a point here, that there's still a negative slope on that, but a lesser negative slope, the tangential deviation still exists, and the signs we got to be kind of mindful of. Okay, so it's really almost like a theta A minus a theta B. If we look at that, it's probably a better way of writing this if I put the signs, kind of the magnitudes of this. Okay, let's see. Actually, let's do this is probably the better way. Theta B minus theta A, because theta B was a positive value here and theta A was a negative value here, and so a minus will get me the value of the two adding together. Okay, so that's what we're going to play, and so this becomes our other formula that we're going to kind of play with. Okay, so that kind of defines our terms that we're looking at. Now, let's go back to our governing differential equation. Okay, in the last video for double integration, we showed you where this formula came from, and again, I said most of the methods for deflections all stem off of some form of this equation. The other one that you saw was that the second derivative of y with respect to x squared, okay, was equal to m over ei. Okay, and this is the guy that's going to let me start playing with this one. This was the other variation of that the change in slope is equal to m over ei. So if I take this equation and I rearrange it a little bit, I can say that d theta is equal to m over ei dx. Okay, and then all I have to do is the change in this angle, if I integrate between point B and point A along this, that if I rearrange this a little bit, that the change in angle between A and B is just the integral of the slope at B minus the slope at A. So this is, again, this formula right here is what this guy is doing for me. Okay, and so that allows me to step into an integral of d theta, so the change in angle. Remember, the kind of basic rules of calculus. All right, and so then if I plug in my formula for d theta dx, that I can rearrange this, that I integrate from position B and A of m dx over ei. Okay, now some textbooks that you'll come across will write this change in angle as something that looks like the change in angle at B with respect to A. Okay, change in angle between A and B is kind of what this is saying. So kind of depending on what your source of reference is, this can be changed. We'll use these interchangeably. I like this notation. Okay, just because it's kind of the change in angle at A with respect to the angle at B. It's kind of the way that's worded. And I like doing this because we'll start looking at figuring out which of the calculations we need to do by using these subscripts as kind of a notation for us to be able to do it. All right, so now we mentioned that he has two rules on this, okay? And so the basic statement that he said is that the change in slope between any 2 points on a continuous elastic curve is equal to the area under the m over EI curve between these 2 points. Okay, and that's all this was doing, was calculating the area under the m over EI curve. Remember, m is a function of x. So if I integrate a function with respect to x, I found the area under that curve, and then EI we assume is constant. For theory, it doesn't have to be, but for over this length, it is a constant over this length. That we can say that change in angle is equal to this. Okay. Now, if a curve is not continuous, the difference in slope is not completely accounted for by the area under the m over EI diagram. Okay, so if we've got something like a hinge in a member or something, we have to do something a little bit differently. And I have an example for more complex situations. But as long as I can write this moment equation as a function of x, we're in business for being able to do some games to be able to play at the slope. And I'll show you how to handle some of those discontinuities and to handle this last point. Okay. All right, the second theorem on here, okay, is we kind of go back to our basic definition. In the last video, we talked about the curvature of an element, and we kind of look at what's happening here. And basically what it boils down to is that if I have 2 points, say 1 and a 2 on this curve, which would be like my A and B on the beam, that there was some instantaneous center of rotation and some change in angle d theta here. Well, I can do some mathematics on this and kind of play with the tangent lines of, the relative to these 2 points that we chose at the end. Okay, and so this could be the difference, at the ends of a dx element along the length of the beam. And we know then that if this is the tangent at this point and this is the tangent at this point, that this angle here, d theta, is the same as the angle of the rotation that was here. And then based off of this, we know that we can kind of start to set some relationships that say that, all right, between B and A, which my A point was here and my B point was here on that original picture, we define that as the tangential deviation at B with respect to A. Okay, and that was this guy. And so we know that between these 2 arbitrary points, 1 and 2 on this finite element, we have what is a portion of this tangential deviation is associated with the change in that angle that's happening on that. Okay, and so what we can say then is that this dt element is basically d theta times x. Okay, it's kind of the way that we can kind of calculate this. And then if I integrate along this curve, I pick up all these little dt values for each of the individual elements, and I can use those to compile the tangential deviation here. Now we know that the angle between these 2 tangent lines we said was the change in theta between there. Okay, but it's this little idea that I can subdivide this guy into little pieces that becomes the power for the second method. All right, so if we say that dt is d theta times x, okay, then dt is going to be m over EI dx. Okay, and then if I integrate between B and A, then I can calculate this tangential deviation at B with respect to A, and I'm going to integrate that with respect to dt. And so all of a sudden now we get BA, and that's going to be m times x over EI. Now m we know is a function of x also. Okay, and so with this becomes the basis for my second calculation for the tangential deviation. So if you notice, it's a little bit different than what you saw on the last one, right? The last one we were just integrating m over EI with respect to x to get the change in the angle, this one over here. But now we've added this extra x that's going to kind of play with our integral when we work it a little bit. Okay, now again, in the book, you might see this written as TA/B. Okay, this is still the tangential deviation at B with respect to A. Okay, and so it's kind of backwards. To me, it's more natural to say it this way. So just be advised. But the basic definition that Moore had was that the tangential deviation at location B on a continuous elastic curve from the tangent line drawn to the elastic curve at a second point A is equal to the moment about B of the area under the m over EI diagram between the points. Okay, now what in the world is that saying? Well, let's suppose that my moment diagram on this element looks something kind of like this. Okay, and I'm looking to find the 2 points that I want. Well, what can happen is I can come in and I can calculate the area under this m over EI curve between those 2 points, and then take the moment that that makes, or the distance, this x bar distance, if you will, on here, which is the measure from the center of that area to the point that I'm looking at. So that's that x bar parameter. Okay, and if we do that over the entire length, now I'm taking, it's almost like a centroidal calculation that you learned back in statics. Okay, but it's kind of a neat little concept for what it is that we're trying to do. So we're going to be doing moments of areas as well as just areas under the m over EI diagram. So right there is our first potential problem that we have. The moment diagrams have to be something convenient for us to be able to work with. Otherwise, this method just becomes very, very cumbersome. It works very well for beams with lots of point loads where the moment diagram may be triangular, because I can handle triangles very simply. But if we get into higher order loads, then this curve and this function, trying to find the centroid of that, becomes a little intimidating. You can do it, you know, and the method will still work, but it's not quite as convenient as when we have simple loads, point loads, and whatnot on our moment diagrams. Okay, all right, so let's give one a shot and see what we can do with it. Okay, so we're going to go back to, and we worked this one last time. Okay, and this is our point load with on the end of a cantilever beam. So we're fixed at A, length of L, point load P acting at point B. Okay, and so we know that the deflected shape, and again, I always try to draw the elastic curve just to kind of give me a sense of what sign would I expect for the slopes or the deflections or something like this. All right, and so here's my elastic curve, is this dotted line, and then at B prime, which would be that point right there, I have a delta B, which is the distance from B to B prime is delta B. Okay, and then that point is going to rotate some amount theta B. Now here's the thing that's kind of cool about this. If we recognize that I need 2 points to look at in order to be able to use this method, clearly B is one of them, because that's the point that I'm after, that I want the information about. Okay, but we got to go find another one that we can work off of, and most often that's the other support, okay, or another support on a continuous beam. So for us, if this is a fixed support, the original undeflected shape was this horizontal line where my pencil is, right? Well, if this is a fixed support, even after it's deformed, it still starts out at that same angle. It's a fixed condition, right? There is no, the delta is 0 at A, and so is the theta is 0 at A. Okay, and so that original position line is still that undeformed position. So that means that the displacement at B, from B to B prime, is a tangential deviation. So we're taking the tangential deviation at point B with respect to the tangent at A. So this line is the tangent at A, right? And then this line is our tangent at B. Okay, and so by definition, if I drop a vertical line between B and B prime, the points between two tangential deviations, or between 2 points on tangent lines, is a tangential deviation, and that happens to be the same thing as delta B. Okay, so that will be our nomenclature. And again, you might see it written as TA, with respect to B. Might be that one, but again, I'm going to use that notation just so we see. All right, so for this particular beam, we want to look at finding the slope theta B and delta B at the tip of the cantilever. All right, so the first thing we have to do is we have to draw the moment diagram, and I'm going to assume that we're okay with drawing these. If you have questions on how to do shear moment diagrams, go back and look at some of our videos in the static series, okay, as well as some of the ones that we've done in this series to kind of help refresh you. But we've got to be able to assume that we can do this part. Okay, this is why shear moment diagrams are so important, is to be able to do these methods. All right, so if that's the case, then this is my moment diagram, okay, which was PL over E, which is the moment for the support was PL, and it's a negative PL. So if we draw a free body diagram, here's my moment. I kind of skipped that step. M is equal to P times L, and it's in a clockwise position, but our beam sign convention says that dude is negative. So we started out at 0, we dropped down to minus PL, okay, and then shear is constant. I'm not drawing the shear diagram. You probably should draw both. But if this is a point load, the shear is constant. It means the moment is first order. This guy is a first order line, or a straight line, that goes from minus PL all the way up to 0. And then all I do is I divide it by EI, because we're assuming EI is constant over the length of this thing. Now, one place where this method really shines is if I have variable cross sections on a beam, okay, that a different I here than a here, or a different E here than here. I can split this beam up, and I can modify the M over EI diagram to reflect that switch, and then we're back in business. But I got to have this M over EI curve. I got to have this guy right here to be able to do it. So that's my curve. So then, if we want the tangential deviation at B with respect to A, it said you find the centroid of this area And then the x bar distance, or the centroidal distance from B to A then for this, if this is a triangle, is just 2/3 of L. Okay, and so from our first theorem, we can do our calculation to find the change in angle of this. The change in angle theta AB is the area under the m over EI between A and B. Okay, well, okay, so this was A and this was B. Okay, so then the area of this is going to be 1/2 of L times minus PL over EI. And so this change in angle between A and B is 1/2 of L minus PL over EI is minus PL squared over 2 EI. Okay, now theta A was 0. And remember, we said that delta theta from A to B was equal to theta B minus theta A, right? Well, if this guy is 0, okay, then theta B is this value. That's the theta B. And that's what we saw in the double integration technique when we worked this example. It's the same thing. And this is really pretty easy to do if you can do this method. It's really cool how this method starts to work out for you. All right, so now we can go in and we can look at calculating our tangential deviations. So again, the displacement at B is equal to tangential deviation B with respect to, or at B with respect to A, okay? And so this is the moment of a triangular area of m over EI about point B. So the point that you're taking it about is the first letter here. Okay, so we're referenced at B, so all of our centroid calculations will be from the center of those areas to B, this first letter on here. Okay, and that's one of the reasons I like to write it this way, is that I know that it's the first letter, and then the second one tells me the other reference point that you're working at. So if we go and we look at this, let's go back to our m over EI diagram then, is we're going to take the area that we calculated between A and B on this, and I'm going to multiply it by the centroid. So we're going to take 1/2 of L times minus PL over EI times 2/3 of L, okay, because that's the distance from the centroid over to here. All right, so if I do that, those are the values that you see in this equation. Okay, so it's 1/2 of L times minus PL over EI, that's the area calculation, multiplied by that x bar distance from the centroid to the point that I want. So we're looking for an x bar B, and this is my area here, okay? And so that then, if you do the math on this, becomes minus PL cubed over 3EI, which is indeed the displacement for the tip of a cantilever. So delta B is minus PL cubed over 3EI becomes the math. Now the minus sign again tells you that your sign convention is downward, because again we assumed upward positive, so down is negative. Okay, and so what this tells you is that the tangent line lies above the elastic curve, okay, for our original reference point, okay, that since the delta A, or the tangent at A was up here and B had moved down here, this tangent line is above this, or that the point is below the reference, okay, is another way of writing that. And so that's the idea. Now, what we can do is we can come in and let's take a look at, let's try another one. And this time we're going to have a beam that has two different cross sections. The moment of inertia of this guy is I, the moment of inertia of this guy is 2I. Okay, and so we can come in and if we wanted to say find the tip displacement, it's the same problem, but what changes now is that, well, I guess it's a different problem. Last one we had a point load. Now I've got a concentrated moment of 100 kip feet on the end of this beam. Okay, and so we know that the moment diagram from statics says that the moment diagram is 100 over the entire length. But because I need an m over EI, what I'm going to do is I'm going to take my 100 and divide it by the I value here. So we're going to divide this by 2I. Okay, so this guy becomes 50 over EI for that segment. Okay, and then the other one is just 1I, so it's 100 over EI here. So you can see how we can change this moment diagram. And then from this, now we just go back and play the exact same game that we did. So again, from A to B was this length, and from B to C was this length. And all I'm going to do is I'm going to basically draw our deflected shape, okay, and in this case we know the deflected shape is going up because the moment is bending, trying to take that point and raise it up, so that's C and this is C prime, okay, and so we can figure out this delta C. Again, it's a fixed condition here, so my reference is still horizontal, so the tangential deviation CA is equal to delta C, and that's going to be equal to our tangential deviation. We're going to say E is 29,000, and then we talked about the I's. Let's just say that I is 400 inches to the fourth as a reference, and that this guy then would be 800 inches to the fourth. Okay, so then all I do is I plug in, and the tangential deviation then is the area between C and A, okay, multiplied by the distance from the centroid of the area to point C. Again, we're going to the first letter on this. Okay, so let's take the first one. So I've got 100 over 2 EI, that's the 50 value over here. Okay, its length is 6 feet for this. And if I'm going to see if it's 6 feet for this segment and 6 feet for this segment, then the center of this guy is 3 feet from B, and B is 6 feet from here. That's where the 9 feet is coming. Okay, and so that's my centroid. Okay, and then the other one is then 100 over EI, and its centroid is at this location, and that distance then is 3 feet. Okay, and so if we look at that, this 100 over EI, and then this times 6 times 3, that would be the moment of the area for that. And then I just add those two pieces together, and so delta C then is 4,500 over EI, and with that I can now go calculate the actual displacement. Now, one thing to point out is you got to watch the units on this, right? Because this moment was in kip feet, okay? And E is in KSI, and I is in inches to the 4, so we've got to kind of do a conversion to get my units to line up, and so that's kind of what we're looking at doing here. Okay, and so again, all of my I guess the moment was in kip feet, and then I have a foot increment value here and a foot increment value here. So there's 3 feet units that have to be converted to inches, and so that's what this 1728 number is. That's 12 cubed. So I'm doing it one for each of the feet that shows up here, here, and here. And when I do that, you can see that the deflection of this beam is going to be then a positive 0.67 inches. Okay, and again, the positive tells you that this thing went upwards as we start to kind of look at it. And so that's how we can kind of start to look at this. Okay, so that's a kind of a simple, get you some of the basics for this particular deflected shape. Okay, now we're going to kind of pause the video at this point, and we'll split this into two, and we'll do some more moment area example problems in the next video. So for now, we'll go ahead and end it. Hopefully this kind of illustrates the basic premise of what it is that we're going to do, and we'll come back in the next video and we'll do some more moment area calculations next time. All right, so as always, if you got any questions, toss us some comments down below. If you found the video useful at all, please give us a like, and then be sure to subscribe, and that'll let you know when the next videos hit. So otherwise, have a great afternoon, and we'll see you guys next time. Happy engineering.